Now let us have a look at the last digit of 8 raised to the power x. Like we did earlier, we'll again draw a circle. Then we put 8 raised to the power 1, 8 raised to the power 2, 8 raised to the power 3 and 8 raised to the power 4 on the circle. We go the anti-clockwise direction starting from 8 raised to the power 1. The last digit of 8 raised to the power 1 is 8, 8 raised to the power 2 is 4, 8 raised to the power 3 is 2 and 8 raised to the power 4 is 6. We draw two lines joining diagonally opposite numbers and extend them. We again proceed the same way we did in the previous cases. For the sake of generalization, we take k equals to 1, 2, 3 and so on and so forth. We write the general powers of 8 in terms of k, whose last digits will be the one as shown in the diagram. And hence, we can easily calculate the last digits of whatever powers of 8. Now let us have a look at the last digit of 9 raised to the power x. We draw a circle first. Then we put 9 raised to the power 1, 9 raised to the power 2 on the circle. We will go the anti-clockwise direction starting from 9 raised to the power 1. Now the last digit of 9 raised to the power 1 is 9 and the last digit of 9 raised to the power 2 is 1. Now we draw a line joining the 2 points and extend them. Again, we proceed in the same way we did in the previous examples. For the sake of generalization, we take k equals to 1, 2, 3 and so on and so forth. We can write the general powers of 9 in terms of k, whose last digits will be the one as shown in the diagram. In this way, we can easily calculate the last digits of whatever powers of 9. The following table gives the last digits of 2 raised to the power x, 3 raised to the power x and 7 raised to the power x for different values of x. The last digit of the different powers of 2 is given as follows. Similarly, the last digit of the different powers of 3 is given as follows. Lastly, the last digit of the different powers of 7 is as follows. The two tables gives the last digits of 8 raised to the power x, 4 raised to the power x and 9 raised to the power x for different values of x. The last digit of the different powers of 8 is given as follows. Similarly, the last digit of the different powers of 4 is given below. And lastly, the last digit of different powers of 9 is as follows. There are a few important points one should always remember while solving the problems on powers. The last digit of 0 raised to the power x is always equal to 0. The last digit of 1 raised to the power x is always equal to 1. The last digit of 5 raised to the power x is always equal to 5. The last digit of 6 raised to the power x is always equal to 6. And the last digit of 10 raised to the power x is always equal to 10. Let us now have a look at the following table, which gives us the last digit of a raised to the power x. After every 4 consecutive values of x starting from 1, the value of a raised to the power x becomes equal to the value of a itself. Any number raised to the power of 0 is always 1. That is, a raised to the power 0 is 1. Let us now put into practice some of the concepts that we have gone through regarding powers. We consider the question, what is the last digit of 7 raised to the power 25? Let us have a look at the table which gives us the last digit of the different powers of 7. 7 raised to the power 25 belongs to the category of 7 raised to the power 4k minus 3, where k is equal to 7. And hence, the last digit of 7 raised to the power 25 is 3. The students should also try solving this problem by the circle method. One of the most frequently asked questions in CAT is based on the concepts of base conversion. Let us now go through this concept. Conversion from the binary or the octal to the decimal system. Now, any number with a base of x can be converted into equivalent decimal number by adding the product of the digits of the number from right to the left with increasing powers of x. Now let us convert 1001 in the binary system to 1 in the decimal system. That is, 1001 to the base 2 is equal to 1 multiplied by 2 raised to the power 0 plus 0 multiplied by 2 raised to the power 1 plus 0 multiplied by 2 raised to the power 2 plus 1 multiplied by 2 raised to the power 3 to the base 10, which gives 1 plus 8 to the base 10, and hence the answer is 9 in the decimal system. Let us now have a look at the conversion from decimal to binary or the octal system. Any decimal number can be converted into a number with a base x by dividing the number by x and then successively dividing the quotients by x. The remainders written in the reverse order gives the equivalent number in the base x. Now let us convert 510 to the base 10 to the octal system. We divide 510 by 8. We get 63 as a quotient and 6 as a remainder. Again, dividing the quotient 63 by 8, we get 7 as a quotient and 7 as a remainder. Again, if we divide the quotient 7, we get 0 as the quotient and 7 as the remainder. We stop when we get the quotient as 0. Starting from the last remainder and going up to the first remainder, we get 510 to the base 10 equals to 776 to the base 8. In this session, we have learned about prime numbers, base conversions, and indices. And I really hope that you have all enjoyed and had fun in learning the number system as well. The following question appeared in CAT 2000. Let S be the set of prime numbers greater than or equal to 2 and less than 100. Multiply all elements of S. With how many consecutive zeros will the product end? We have to choose the correct alternatives from the given options: A 1, B 4, C 5, or D 10. We know that no prime number ends in 0. So, for the product of the prime numbers in S to end in zeros, there has to be a multiplication of the multiples 2 and 5, with 2 and 5 being the last digits. The only multiples of 2 and 5 which are prime numbers are 2 and 5. No other prime numbers have 2 and 5 as their last digits. And hence, the number of zeros with which the product ends is 1, contributed by the 0 in 10 which we get by multiplication of 2 and 5. And hence, the correct answer or the correct alternative is A, that is 1.